Hey, welcome everyone. This is the Platonic Academy of Melbourne, Platonic Esoteric Geometry, Autumn 2021, Week 6. So these are the slides from the first part of the talk. Most of Week 6 in the autumn session was the geometry of music, which was presented by Eric Timewell. So what I'm going to do here is just give the slides for the first part, which covers some unifying themes, unification under the notion of emanation from the one by means of perhaps a logos. So I'll just start off with a couple of quotes here. This is from Epinomis, which is the considered to be an addendum to Plato's Laws that was possibly written by Plato, but maybe at least an early academic document. To crown it all, we must go on to the generation of things divine, the fairest and most heavenly spectacle God has vouchsafed to the eye of man. Every geometric figure, system of numbers, composition of harmonies, and the regularity in the revolution of the stars must appear to one who properly learns to be one in principle in all cases. And it will so appear if, as we say, one learns correctly, looking to one thing, for it will appear to them on consideration that there naturally exists one bond of all things. Now, if we go to the Timaeus, which was one of Plato's later works, soon after Timaeus, the Pythagorean astronomer, establishes that the emanation of all living beings is from one living being, he considers the bond between all things and says, the most beautiful bond is one that brings perfect unity to itself and the parts linked. And this is most beautifully done by analogia, which we've already come across. So that's like a geometric series, as we'll remember. And back to the Epinomis, or rather I should go back to the Laws. In a celebrated passage of Plato's Laws, the anonymous Athenian, who's usually considered to be Plato speaking for himself, implores that we must continually put this problem to each other and give our love of victory a pastime worthy to us. So what is the problem, the victory that the anonymous Athenian says that we should strive for? He says that to know the generative nature of the symmetrical and the asymmetrical in relation to one another. Now I've just translated symmetrical and asymmetrical as commensurable and incommensurable. So remember, the commensurable numbers are the normal numbers. The incommensurable measurements are like the diagonals, like the square root of 2 and square root of 5, and all those diagonals that aren't perfect squares. So to know the generative nature of symmetrical and asymmetricals in relation to one another. So to bring the geometry all together in one unifying system. And in the Epinomis, plane geometry is redefined as a manifest assimilation to one another of numbers that are naturally dissimilar, affected by reference to area. So the reference to area is like in Pythagoras' theorem, where you get the areas on the sides that give you the diagonal, irrational, or asymmetrical values. So there we go. There's a lot of hints in Plato's dialogues, and then in Middle Platonism and the textbooks of Platonism that are coming out of the tradition of the esoteric geometry in the academy that point towards this as their unifying project to see how everything emerges from one and through a particular elementary medium. And that medium is often called logos. Okay, so you know, we've already talked about this emanation in the metaphor of the point generating the line as it moves in time, and the line generating the plane, and the plane generating the solid. And so that's the first time which we get into our sensible experience, because everything in our sensible experience is in those three dimensions. But what is the means of this emanation? I mean, the point moves, it generates a line, but how do we get all the difference? And so this is something that they were very interested in investigating. And you will remember us talking about the medium of the logos, meaning ratio in this case. So we've talked quite a bit already about how logos is fundamental to this geometry, and how all the geometry and its relations to each other seems to be related by ratio. So even angles would be expressed in terms of the ratio of the right angle triangle that gives that angle. So it would be given as we would give gradients sometime, like 1 in 40 or 1 in 10 or 1 in 1 for a 45-degree angle, that sort of thing. And we've also considered analogia or proportion. So we'll have a bit more of a look at proportion now. So I'm just going to share the screen. Okay. So here we go. Now, let's start in a slightly different way. Let's start in terms looking at what's called a four-term proportion. So this is where A is to B, if you want to use the algebra, as B, C is to D. So I'm just giving it initially without the numbers, which can be a bit scary at first. It's really just talking about the sorts of things that we deal with all the time, like a scale model of a ship, or scale model of anything, or you know, television image in a big screen, a small screen, or a graphic. So if you reduce it, you need to keep the proportions the same, otherwise it looks a bit weird. So here we've got a ship and a scale model of the ship. And so the height of the mast, A, is to the length of the ship, the larger ship, as the height of the mast, C, is to the length of the smaller ship, which is D. So A is to B, height of the mast is to the length, as on the smaller scale, C is to D, height of the mast is to the length. Okay, and we can also say that A is to C as B is to D. Well, so we've mixed it up a bit. What does that mean? Well, the height of the mast on the larger ship is to the height of the mast on the smaller ship, just as the length of the boat is to the length of the boat on the smaller ship. So they have to be in proportion to be in scale. So both those ways of dealing with the proportion work. Okay, and so proportion is very important for us in our perception when we see maybe an animal at a distance smaller, and when it's closer, we can tell perhaps that it's a cat and not a fox, or a Tassie tiger maybe, and not a fox or something like that. And we tell these things often, especially when the light is bad, we tell them by their proportions. Well, it's got the proportions of a cat, it hasn't got the proportions of a fox, and so on. And so this sort of thing is very important for us in our perception. So we'd have the statue of David here, and people say, oh, it's so beautifully proportioned. But hang on, maybe the hands are a bit big. We notice when the proportions are wrong. So we might see an old medieval painting where the head's a bit small or something, and you really notice it, or a children's drawing or that sort of thing. So proportions are something that we really important, and we notice. So think of the proportions of a face and how we recognize so many different human faces by subtle differences in their proportions. Now, let's think of this in terms of number. So if we're talking about the 4-term proportion, we can see that they could be considered to be pulled out of a geometric series. So I'm going to jump into the geometric series now and look at 4-term proportions there. So here we've got 2:4 as 16:32. So they're both in the double ratio. And we've got 1:3 as 27:81. So they're both in the triple ratio. Okay, and so we can find various relationships between them. So A is to B as C is to D, like the two masts are to each other as the lengths of the boat were to each other. That's that one. And A is to C as B is to D. That's like one mast is to the other as the length of the boat is to the other. And there's also other interesting relations, including that if you multiply the first and the last of the terms, so A times D equals the same as multiplying the two middle terms. And you can see this here on this screen working for the double ratio. A couple of examples in the double ratio and a couple of examples in the triple ratio. Okay. Okay, and of course we can see that we can then come down to what we've looked at before, which is a 3-term proportion or a geometric mean. So this is where the middle term is shared. This would just be 3 terms in a geometric series. That's another way of seeing it. So here down the bottom, we've got A is to B as B is to C. So it's just 3 terms, A, B, and C, where the, for example, 1:2, just as 2:4, or 9:27, just as 27:81. They're both in the triple ratio, and the 2 is the geometric mean of 1/4 in the double series, and 27 is the geometric mean of 81 and 9 in the triple series. Okay, so now consider what is the geometric mean between the two measures 1 and 2. So we know what the geometric mean is between 1 and 4. Geometric mean is 2, right? Because double 1 is 2 and double 2 is 4. But what's a geometric mean between 1 and 2? Now, it's not the arithmetic mean, which is a bit like the average. So the average of 1 and 2 is 1.5, halfway in between in terms of distance, if you like, or straight measurement. But that's not the geometric mean. That's not halfway by ratio. So what is halfway by ratio? Well, you might remember we found the halfway by ratio in the same way that we found the doubling of the square. And so halfway by ratio between 1 and 2 is the square root of 2. So 1 times the square root of 2 equals square root of 2, and square root of 2 times square root of 2 equals 2. Okay, and this is actually the diagram that we find in Plato's Nemo dialogue, where the slave boy works out on his own with direction from Socrates how to find solve the problem of the doubling of the square. Okay. It also gives the geometric mean between 1 and 2, which is the square root of 2. As we found, a very important number. 1 is to root 2 as root 2 is to 2. And this square expresses, in a way we can see how this square expresses the whole series, because it's given the first 3 terms. And once you've got the first 3 terms, you can then move on and give the whole series. So that's quite important to see here how the geometric series is given in one diagram. The means of generation is given in one diagram. Okay, so the geometric series will be important for music, as we'll see when in Eric's presentation. Okay. Now, what would be, so we've seen a 4-term proportion, A is to B as B is to C. We've seen a 3-term proportion, A is to B as B is to C. So 1 is to root 2 as root 2 is to 2. What would be a 2-term proportion? What would that look like? Okay, so a 2-term proportion is where A is to B as B is to A plus B. So here we've got A is to B, the small part of a line cut at a particular point, is to the longer line as the longer line is to both of them together. The ratio of the small part to the larger part is the same as the larger is to the whole. Okay, and as we might remember from last week, this is the golden ratio, as we call it, or division by extreme and mean, as Euclid called it, when it was first revealed. As far as we know, Euclid was the first to publish the way to determine the golden ratio, as we call it. And on the right-hand side, that shows how he determined it, and in fact how we determined it last week when we started to build our golden spiral, which we just have a bit more of a look at that now. So there's different ways of expressing these proportions, but if this is 1 here, then this is the inverse of the golden ratio, or the inverse of phi, and this is phi. So inverse of phi is to 1 as 1 is to phi, which is amazing, really. And it's interesting in its expression in numerically as well. So the inverse of phi is 0.62, and phi itself is 1.62. Okay, doesn't happen with other ratios. All right, so 1 over phi is to 1 as 1 is to phi. The ratio of the small part to the larger part is the same as the larger part to the whole. Okay, and here we can see it in the diagram we drew last week. Okay. Now, why is this interesting? Because one reason it's interesting, I mean, there's so many ways that the golden ratio is interesting, and we won't have enough time to go into all the different ways in the books that we've had in the room, show all the different ways that this ratio is fascinating and expressed in nature. Okay, but one way it's important is that it expresses it expresses a generation and emanation by logos in a single diagram. So here we've got, if you like, just one line cut in a particular way expresses the geometric geometric mean, and therefore the geometric series. So you've got the first three terms of the series. Already you've got the ratio within the origin. Now, I like to use the prologue to John's Gospel to explain what they were trying to work out in these terms. So, if you have an origin, which was sometimes called principle or arche, the original one. And the original one creates all things, right? Now, if it creates all things out of matter, right? So you have God and he's got matter and it's like clay and he makes everything out of clay. Well, there's God and then there's clay. And that's not a monotheism. That's not everything absolutely coming from the one, because there's already the clay as well, right? So something must have created that. And so ultimately, when you're explaining things in this monist or monotheistic way, monotheistic emanationism, you need to have the one creating from itself, right? And so it has to create from itself, and its means of creation have to be within it. And so if we go back and look at this ratio here, we could say that if this is an analogy for God or the original one, then as it is cut, it already has within it the means for the generation of its differentiation by further cuts. Okay. And so we can see this principle of generation by a logos in an expression like the famous prologue to John's Gospel. Now, people who were brought up in the West, rather than with the original Greek, would remember the translation, in the beginning was the word. Now, logos can mean a lot of things. It can mean discourse. It can mean ratio, as we see it here, but rarely translated as word. So it was kind of like a distracting thing. So if we go back to the original logos and we think of it as the means of generation, because that's the way it was thought of in early Christianity and in Stoicism and in some early Platonism, it's the means of creation. And so in John, prologue to John's Gospel, it says, in the origin was the logos, and the logos was with God, and the logos was God. The ratio was God. Okay, so remember the divided line in the golden ratio. It already has the ratio within the origin. So the ratio, the means of generation, was God. The logos was in the origin with God. All things came into being through him, and without him, not even one thing that came into being came into being. So this is the principle of generation from an original one, principle by means of a logos that is inherent within the origin. So this is the sort of important principle that the Pythagoreans and the Platonists and early Christianity subscribed to. Okay. So there's the line. So cut in the origin, at the same time, it has its means of generation, its logos of generation, which is the line so cut. All right. Now, talk a bit more about the golden ratio. I'll go back again to this length for width substitution. So remember, we were doing side for diagonal substitution when we were doing the doubling of the square. This is length for width substitution. So where you start off with a square like this, which we will find out is important for the golden ratio, a square where one side is double the other, and then you substitute the length for the width. So the long side here then becomes the width of the next rectangle, and you see how it's orientated gone around anti-clockwise 90 degrees. So 1:2 is 2:4 in the double ratio. And then 4 then was the width, and now it becomes, sorry, the length, the long side, and now it becomes a short side in the new rectangle, turned around 90 degrees again, going around anti-clockwise. We can keep going, where 8 is the short side and 16 is the long side. So this generation goes around in a cycle, anti-clockwise in this case, in the double ratio. Now, this is often called logarithmic progression or spiral. We haven't drawn the spiral in as we drew in last week with the golden ratio, but you can do this with any ratio. Some people think it's just something special about the golden ratio, but you can do this with the double ratio or the triple ratio or 1.5 ratio or whatever, and get a spiral that will be tighter or more expanded, but it'll still be the same sort of spiral. Okay, so now if we look at the golden ratio, we can see that we've got a similar spiral here. And remember that when we drew our spiral, we started large and came down, and we can see that that is easier to do, to draw, because once you get that first square, now I've just superimposed, sorry, the first golden rectangle, I've superimposed Euclid's diagram there, which is the same thing pretty much that you did to start off doing your spiral. So we've made our first golden rectangle there, where the ratio of the side, the width to the length is the golden ratio. Now, the way we drew our spiral was we drew it in terms of continuing to build squares inside golden rectangles. So let me show this. So we went back to the original square that we built before we built the golden rectangle, and we'll see that over on the right hand side here we've got another smaller golden rectangle. Okay, now we can use this side at the top here to measure down and get our next square. Okay, and then what remains is a golden rectangle. See how, again, it's orientated 90 degrees clockwise in this case. And so there we can see again, measuring from this side, that's what we did. We measured from that right side there and made another square inside that golden rectangle. And then we got another one, turned around another 90 degrees, found the square in there, and golden rectangle, found the square in there, found the square in there, and kept going on and on and on. And that was the basis on which we drew our spiral, as you remember last week. All right. Now, and we will remember that the spiral, the golden ratio is related to the pentagon. We haven't explained exactly why it's related to that and how, but we do know that when you draw the pentagram beside it, that all of these different lengths that we get inside the pentagram are all in ratio with each other. And this was a secret passcode for the Pythagoreans, the pentagram, because it had this special ratio within it. And the key, there's so many different ways in which this ratio is expressed, but if you take this length here, this short length here, horizontal length, and compare that to the long length on the other side there, or in here in the smaller part, that is in the golden ratio. And then A is to B as B is to C, that's the same. And then it works here as well, C is to D. So there is a ratio between this A and this D there, and the E here, and so on. So all the different line segments here are in ratio with each other. Okay, and this is related to expressions we find of the golden ratio in nature. And so as Kepler said, that the flower is kind of like a flag, like a symbol of the golden ratio, expressing how propagation and self-development in nature occurs. Okay. All right. Now, I just want to go back to the spiral of Theodorus and see if we can see how the golden ratio is related to all of these other diagonal numbers, all these other square roots. Now, remember, we generated these one from the other in this spiral, so we can see how they are symmetrical with each other. Remember, it's all about bringing everything into symmetry with everything else and seeing how everything can be generated from everything else. So remember how we got from the monad square, we took the diagonal and we drew this right angle triangle with a unit length, and using Pythagoras' theorem, we found out that its hypotenuse is the square root of 3. So square root of 2 squared equals 2, and 1 squared equals 1. So 2 plus 1 equals 3, and so the diagonal is the square root of 3 according to Pythagoras' theorem. And the way they were thinking about it is that each of these triangles had plane squares off their side, and so we can see that each one would have the square off their side there. But they also what's important is to think of this rectangle here, which is the rectangle with side root 2 and 1. So the area of that is root 2. And what's this like? Do you remember this? This is like the A series in paper. So A3, A4, A5, A6, A0, A1, A2. All of these, if you call the short side 1, then the long side will be root 2, and the area will be the square root of 2. So that's a very important shape. Now, I want to show you how root 5 over here is related to phi, to the golden ratio. Now let's have a look at this square here, which is the square on, the rectangle on root 4, right? So rectangle on root 4 gives the next line root 5, but what is this rectangle? Square root of 4 is 2, so this line here is exactly 2. This line here is 1, so this is a 1, 2 rectangle that we had before, as you remember when we were doing our first logarithmic spiral. So look at that. 1, 2, length of 2, width of 1, and then by Pythagoras' theorem, we work out that the diagonal is root 5. Okay. And it's just the same as what we were working with earlier. All right. Now, how does this relate to the golden ratio? Well, let's have a look at how we generated the golden ratio earlier. And notice this rectangle here, which is where we cut in half our original square. Now that length, if the monad square is 1, so it has sides of 1, then half is a half, and so it's a half is to 1. So a half is to 1 is in the same ratio of 1 is to 2, right? Double half, you get 1, double 1, you get 2. So the half by 1 is in the same ratio as 2 by 1. Okay, it's just in terms of the measurement we've done, it's just half the size. Okay, but it's basically the same rectangle. So we can actually compare the measurements of the two rectangles. Now, if this is half by 1, we also know that this length, what this diagonal here is in terms of phi. And we can see that this length here, okay, is the inverse 1 over phi. And we can see here that this length here is half. Okay, so we've got 1 over phi for that length there, and we've got half there. So the diagonal is half plus 1 over phi. Now remember, this rectangle is half the size, right, of the root 5 rectangle. So if we doubled this, then we would get root 5. So 2 times half plus the inverse of phi from this diagram equals root 5, because this is a half by 1 rectangle, and this is a 1 by 2, double its size. So double the diagonal and you get root 5. And that, it can be expressed in different ways, is the direct relationship between root 5 and phi. It's kind of two ways of saying the same thing. Okay, and so that's then, as we remember, related to the pentagon and pentagram and related to its natural expression. So we can kind of see how things are connecting together a bit here. Okay, so all diagonals are related in these geometric expressions, not arithmetic expressions. We try to express them arithmetically, remember, and the ratios don't work, right? You can never express the square root of 2 as a ratio numerically, because like in the decimal system, the fraction just keeps going on and on and on. So square root of 2, I think, is 1.42, so on, so on. Just like pi is 1.3, 3.14, and so on and so on. So, but we can express these geometrically in relation to each other. So remember how we expressed the circle inside the square expresses the diagonal of the square and the circumference of the circle in relation to each other. And here we've expressed all these diagonal numbers, and it can keep going round and round in relation to each other. And then we've shown how the golden ratio is related to root 5 in this spiral. So we can see how all these logos, all these ratios are starting to relate to each other in just a little bit of geometry that we've done in this course. And then, of course, that relates to some natural expressions. Okay. So that's probably enough on connecting all that together. Now I want to spend a little bit of time on number, right? And so we've been doing all this geometry. We haven't done anything on number yet, and fair enough. But number is geometric. Okay, what's the difference between number and geometry? Well, number is temporal and discrete. It's in time and it's periodic, we might say. Now, remember how I was saying how is a line made up of points? Well, a point has no length, so it can't be. Was it made up of really tiny points? No, it can't be. According to Platonists and the Pythagoreans, a line is continuous, is a point moving in time. But we can analyze a line numerically. So we can use number to make little measures and analyze it numerically. And that's what they did with the infinitesimal calculus. Remember when we were talking about that, where they were trying to measure the area under a curve, and they thought if they draw little rectangles, they can add up the areas of all the rectangles, and then you approximately get the area of under the curve. But of course, it's not perfect. If the rectangles get narrower and narrower and narrower, then it gets closer to the true value of the area under the curve. Now remember, it's only actually when they get to 0 that it works, but then it doesn't work because at 0, the rectangles have 0 width and so no area. So it gets a bit crazy, and this confused people at the time. But what it is it's a way of getting to that area. So in the same way, we can think of a line as continuous, but we can also get towards it or imagine it digitally, if we like. And digital is a good way of thinking about this, not digital as in 10 fingers, digital as in computers, if you like. So you imagine, we imagined a camera taking a photo of an oil painting. So the oil painting's continuous, right? It's all that oil hardened on the canvas. And then we can use a camera with quite large pixels because it's a very primitive camera, and it'll give a fair representation. And then we use smaller and smaller pixels until we get the sort of cameras of today with these amazingly tiny pixels. And as the pixels get smaller, it's getting closer and closer to a true representation of the oil painting, right? And so, but we don't make the mistake and say that when the pixel gets infinitely small, then it is the oil painting. No, it's a representation or an analysis. It's an analysis of the painting. So we need to draw the distinction between the analysis of the geometry and the geometry itself. The continuous line and breaking it down into smaller and smaller lengths, as you would do in the infinitesimal calculus. Okay, so that's how we can imagine the line as a series of points, but we're imagining it. It's not its reality. Now, with counting, however, counting, of course, is periodic, discrete, and in time. So it's, when we think of the counting, we think of it in an ordinal way, as having an order. So when you're counting things, you have to count in order. So when you're going 1, 2, 3, 4, 5, you're actually going in a primary way, according to the Pythagoreans, first, second, third, fourth, fifth, one after the other. In order to count things, if you're counting things, you need to order them. Think of cattle moving around in a pen, right? You kind of have to put them through a gate and count them as they go through a gate, or otherwise you'll get completely confused. You need to count them in order. But how does counting start from the original one? Remember, in the Republic, the origin of the mathematical science, the formal origin of all, is a special one that has its other, not one or none, close by. So how does this one, none, same other, where the other is in the same, remember the island and the sea, the other is in the same, it's part of the same. So how does this one that also has in it its none, right? How does that generate all? Well, let's think about that. And think about it in terms of one of our analogies for counting. Oh, sorry, for the distinction, for the simple unity, which was island and sea, and perhaps island and sea on one island on a sphere. So remember, this is an unlimited limit. So we've got the red, and then we've got the distinction between red and white, and there's no other limit. If I drew this on the whiteboard, there would be the limit of the border of the whiteboard. But here, there's nothing. What can we do here? What can we do here in time? Well, what we can do as an analogy for this counting is we can move from, say, the red to the white. You might say God to not God. So we cross from one side to the other. Same, not same is other. Okay, use whatever terms you like. And what's not other? Well, it's back to the same. And what's not same? Other. Not other, same. So we can think of this alternation. And because this alternation's in time, we can also think of it as like walking, left, right, left, right, left, right. Right is the opposite to left, left is the opposite to right. And we'll remember how in Plato, I've said how Plato, when he's talking about the counting numbers, he talks about the alternation of the opposites, odd and even, and often uses odd and even as examples of the opposites. Okay. So the last thing I want to do with number, because this is just a simple introduction to their number, there's a lot more to say about it, is to talk about higher degree counting. Now, we usually think of higher degree counting in terms of, say, squares, like a number like 2 squared, or 2 to the second degree is 4, and 4 to the second degree is 16, or 2 to the third degree is 2 cubed, which is 4 times 2 is 8. Yeah. So we talk about degrees in terms of squares, but they did it in terms of squares, but not just in terms of squares. So I want to show you a more elementary one that they did. So if you imagine counting just in a line like this, these are the periods. So there's 1, and so the odd and even isn't so important at this stage. It is important, but not in this explanation. So we go 1, we go 2, and then we go 3, and then 4. Okay, so we've got the series, and that can just keep going on and on and on. Now, if we look at each number there, we can say, well, there was the 1, and then there was the 1, 2, and then there was the 1, 2, and 3. Okay, so we've got all those numbers together. Now, if we stack them on top of each other, right, then we get a plane number. And this is a plane number in the triangular series. So if we do the next one again, we get a very special plane number in the triangular series, which is the tetractys. And we'll talk about that in a minute, but that is where you've got 1 at the top, and then it's stacked on top of 2, stacked on top of 3, get this right, and then stacked on top of 4. A bit neater. Okay, so there's the tetractys as a stacking of the first 4 numbers. Okay. Now, this stacking can continue, right? So that's from linear numbers to the first plane number. Now, imagine if you stacked the plane numbers. So the first plane number is 1. The second plane number is that 3 there. And the third plane number is this 6. Right? So there are the first three plane numbers. Now, if I stack them, I get the third solid number in this triangular pyramid series. So there we've got the triangular pyramid. So the first triangular pyramid number is 1, right? The second one is 3, and the third one is 3 plus 6 is 9. Yep, 9. Okay. So that can also occur, of course, counting in squares. So I'll quickly show the square counting. It starts in the plane. So the first well, let's start with the monad, and then the first square number is 4. Okay, that's your first square. And then the next square number is 9, 3 by 3. So 1 by 1, 2 by 2, and then 3 by 3. Okay, so they're the square numbers. So I can put them beside each other here. That's the second square number, or the first proper square number. And there we've got the series there, 1, 4, 9. Stack them, right? We get, in this case, the third square pyramid number. Okay, so there's the second square pyramid number, and there's the monad origin. So you can see by this sort of stacking principle, there's other ways of expressing it. You can see that they built their higher dimensional numbers. Okay, and these two series, there are other series, but these two, the triangular series and the square series, were the most important for them. All right, now I'll share the screen and show you a bit more about that. Okay, all right. So they called these gnomic expansions because they used a set square, which was called a gnomon in that time. And so if you imagine with a pebble in the sand, they put their set square there, and that told them where to put the next pebbles. So this is the square series. We've gone from the monad origin to the first square number, to the second square number, and to the third square number, and so on. Okay, the most important was the first one I did, the triangular series, and the first 3 4, if you count the origin, members of the triangular series make the, or the fourth number in the triangular series makes the tetractys, which was another one of these secret esoteric symbols of the Pythagoreans and the Platonists. And in the tetractys, or in this triangular series, the gnomon is a straight rod, and it has the same name as the rod, still the same name today, that's used for the sundial. And the legend is that Thales, the first scientist in the 6th century BC, the first Greek scientist, brought the first scientific instrument, the rod for the sundial, back from Egypt with him. And so you can imagine the Pythagoreans taking that rod and laying it on its side and building their triangular series, especially their tetractys. So it's the fourth in the series. It's an equilateral triangle, and it was considered to have these special ratios, as Eric will explain why they're important in music. And they're important in many other ways as well. 1 is to 2, 2 is to 4, and 1 is to 2, 2 is to 3, and 3 is to 4. Important ratios in music, as we shall see, but also important in many other ways. Okay. And here's just some images of the stacking. So we've got how cannonballs, or whatever they are, oranges, can be stacked in the triangular pyramid. They can also be stacked in the square pyramid quite easily. But these series have very interesting other qualities that we won't go into today. Okay, and it's just to give you some sort of visual suggestion, we can see how we can move between the triangular series here. So we've got that on the left, it's generating out from the original one. Okay, and I'm relating that as we move across here to the continued fraction. I don't know whether people know continued fractions, but the golden ratio has this very special simple continued fraction, which is 1 over 1 plus 1 over 1 plus 1 over 1 plus 1. And there's a relationship between, as we can see, perhaps visually here, between the triangular series and the continued fraction for phi, and in this case, the inverse of phi. All right, I think that's all I have for you before Eric presents his music. So I'm going to leave the recording here, and hope that was helpful for you in your revision or whenever this is used. And I'll bid you farewell until we see you next time in one of our other Platonic Academy classes. Okay, bye.